Okay, so we're going to get started in just a few minutes. As people are sitting down, coming in, make sure to fill out this Astro check-in form, tinyurl.com/astro-check-in, or scan the QR code. This helps us. It's working? Oh. Is it okay with this? Okay. I do have the volume up.
I can hear it.
Yeah. In the back, can you hear this? Good? Okay, I can try to project as well as talking to this. Yeah, so we will be doing a raffle of Columbia Astronomy merchandise later tonight during the Q&A. So in order to be eligible for the raffle, you need to fill out this Astro check-in form. So I'll give you another minute to open the form if you haven't yet.
I forgot my charger. Do you think my laptop is going to die? No, that one.
So.
An Apple one? Yeah. Sorry. I just thought of it. I was like, oh, it definitely has happened. Sorry. Yeah, I think that will work. Let me try.
Okay. All right, so we're going to get started. Welcome everyone to another Public Astronomy Night. Thank you all so much for showing up. Tonight's event is going to be a bit different than usual because on April 8th, in just over 2 weeks from today, there's going to be a total solar eclipse passing through the contiguous United States. So we're actually going to start today by doing a little bit of eclipse-related trivia and also talking a little bit about the upcoming eclipse. Then we're going to move on to the main topic of tonight, black hole paleontology. We'll have a few related trivia questions for black hole paleontology, and then we'll hear from our main speaker, Dr. Broekgaarden, who's going to talk about her research on black hole and gravitational wave paleontology. After this, we're going to do a Q&A with Dr. Broekgaarden, and during the Q&A, we're going to raffle off some official Columbia Astronomy merchandise. Very exciting. Then after that, we'll break for a reception, where you can ask Dr. Broekgaarden questions one-on-one or talk to any of the other Columbia astronomers in this room right now or tonight. If we're extremely lucky, we'll be able to do some stargazing. The moon is up and bright, but it's a little cloudy. So fingers and toes, everything else crossed. We'll see. We'll check in 30 minutes and see how it's doing. It's good to remain optimistic. But so to get things kicked off, we have some special eclipse trivia questions that I'm going to read out, starting with question 1. So on April 8th, 2024, a total solar eclipse will pass over a large strip of the contiguous United States, starting in Texas and ending in Maine. Which of the following best describes a solar eclipse? A, the moon passes between the Earth and the sun, blocking out the sun's light. B, the Earth passes between the sun and the moon, casting a shadow on the moon. C, the sun, Earth, and moon form a right angle, illuminating half of the moon. Or D, the sun passes between the Earth and the moon, ending all life on Earth. So, do we think the answer is
D, right?
A? Hands raised for A. Hands raised for B? For C? Or for the very special D? Okay, some D. So the answer is A. The moon passes between the Earth and the sun, blocking out the sun's light, and this is what's going to happen on April 8th. Question 2. The total solar eclipse on April 8th will pass over upstate New York, covering such cities as Buffalo, Rochester, and Syracuse. When will this total eclipse begin in Buffalo? A, at 2:45 p.m., B, at 3:16 p.m., C, at 4:19 p.m., or D, at 5:04 p.m.? So, hands raised for A, B, C, or D? Even spread. Totality, when the moon completely covers the sun, will start at 3:16 p.m. and will last 4 minutes. Okay, question 3. While the eclipse's path of totality will not cross through New York City on April 8th, observers in the city will still be able to see a partial solar eclipse. So at the peak of this partial eclipse, how much of the sun will be covered by the moon? Is it A, 50%, B, 78%, C, 89%, or D, 98%. So Ray stands for, oh, well, I didn't give her the answer. Let's see. Okay, Ray stands for A. Ray stands for B. For C? Impressive. Very impressive. Or for D, anybody? Okay. Somehow you all got the right answer. It was C, 89%. Question 4, the penultimate question. So when is it safe to look at a partial solar eclipse with your naked eye? A, it's always safe because my eyes are simply built different. B, when more than 50% of the sun is covered by the moon. C, when more than 80% of the sun is covered by the moon. Or D, never. Okay, Ray stands for A. Okay. Some very special people over there. Ray stands for B, C, and D. Yeah, as we'll talk about in a little bit, it is never safe to look at a partial solar eclipse or a total solar eclipse when it's not in totality without eclipse glasses. Okay, and the final question before we delve a bit more into the eclipse. After April 8th, 2024, when will the next total solar eclipse occur over the contiguous United States? A, August 12th, 2026. B, November 25th, 2030. C, August 23rd, 2044. Or D, January 32nd, 2050, following the Great Calendar Reform of 2049. So Ray stands for A, for B, for C, or for D? Cool. Okay, the answer is August 23rd, 2044. So, okay, let's recap a little bit of what we just talked about in a little bit more depth to try to answer this question. What is happening on April 8th, and why is it such a special event? So, on April 8th, a total solar eclipse will be passing through the contiguous United States. So, the moon is going to cast a shadow on the Earth from the sun. All of this depends on the geometry of the Earth, the moon, and the sun together. So, if we have the Earth between the moon and the sun, then the Earth will cast a shadow on the moon. The moon will look reddish, and we get a lunar eclipse, which is pretty cool. Or, if the moon is between the Earth and the sun, then the moon will cast a shadow on the Earth, and we'll get a solar eclipse. This is what we're going to see on April 8th, and it'll be very cool. Or, if the sun is between the Earth and the moon, we get the end of all life as we know it. Thankfully, this has a very, very, very small chance of happening, hopefully. But today we're focused on this middle geometry, the solar eclipse. And actually what's happening on April 8th, the total solar eclipse, is a bit more complicated than what's shown in this little cartoon here. There are a number of criteria that have to be met in order to get a total solar eclipse. So first, we need to have the right phase of the moon. We need the moon to be between the Earth and the sun such that it blocks out the entire disk of the sun as seen from the Earth. So we can't have a full moon, we can't have a waning crescent, we can't have a waxing crescent. We need that perfect new moon right between the Earth and the sun. But this is still not sufficient for a total solar eclipse because this is complicated by the fact that the orbit of the moon around the Earth is actually slightly inclined. It's at a slight angle to the orbit of the Earth around the sun. So even if we do have this lineup of the Earth, then the moon, and the sun, there's still a probability that the moon will be a little too high or a little too low on the sky, and it won't fully cover up the sun, and we get a partial eclipse. So we need the moon to be on what's called the nodal axis, or the line of nodes, in order to get this total solar eclipse. And fortunately, at 2 points during the year, at 2 points during the Earth's orbit around the sun, we do have the moon along the line of nodes. So at the top of the diagram and at the bottom of the diagram, the moon is along the line of nodes. It's at the correct altitude. But to the left and to the right, we have the moon either a bit too high on its orbit or a bit too low on its orbit. So in those cases, we'd get partial solar eclipses. Now, even this is not sufficient to get a total solar eclipse. In addition for the moon being on the line of nodes, we also have the fact that the moon's orbit around the Earth is not completely circular. It's elliptical. So, at some points along the moon's orbit, the moon will appear slightly closer or slightly further away from the Earth on the sky. So if we happen to have the moon along the line of nodes, but the moon is a little too far away to match the size of the sun's disk, then we end up with what's called an annular eclipse. Still very beautiful. It's this image in the middle. But if all these conditions line up right, we have a new moon where the Earth, the moon, and the sun are all aligned. The moon is along the line of nodes. The moon is at just the right distance along its orbit to match the apparent size of the sun on the sky. We get this beautiful total solar eclipse. Truly a special and rare event. And actually, there's no innate physical reason for this to occur. It's a complete coincidence that the angular size of the moon, as seen from Earth, and the apparent size of the sun seen from Earth are very, very close together. If we were to go to another planet like Mars, we would actually never get a total solar eclipse. We'd only get annular eclipses because we don't have the same serendipity of the same apparent size on the sky. So this is really a special event, and it's an event that we can see from the contiguous United States on April 8th. So here's a map of the US, and this band through the US is the path of totality. If you're in this band, then you will see that beautiful total solar eclipse. This passes through Dallas, Texas, Burlington, Vermont, Syracuse, and Buffalo, New York. Unfortunately, it doesn't pass through New York City, but New York City is close enough to get a fairly substantial partial solar eclipse. As we saw earlier, 89% of the sun will be covered by the moon at the height of the partial eclipse. And so if you're staying here in the city during the eclipse, always have your solar filter or your eye protection, your solar eclipse glasses equipped when looking at the partial solar eclipse. It is never safe to look at the sun without it. The shadow cast during the eclipse will dilate your pupils, but also there's still some sunlight that leaks past the moon, and that'll damage your retinas. So we do have a bunch of solar eclipse glasses for you tonight. At the very end of the events, after the Q&A, if you want to pick up a solar eclipse glasses for either the partial eclipse or the total eclipse, you can get them tonight. If you do travel to the path of totality, so say you're in Buffalo or Rochester, New York, the total eclipse, well, the eclipse will start at 2:04 p.m. That's when the moon starts to move in front of the sun's disk. Totality, when the moon starts to completely block the solar disk, will start at around 3:16 p.m. It'll last 4 minutes, finish around 3:20 p.m. And then the eclipse will finally end at 4:32 p.m. when the moon finally exits the transit past the sun. And remember, when the eclipse is not in totality, when you can see any sliver of sunlight, it is still not safe to look at the eclipse with your naked eyes. You will still need a solar filter or solar eclipse glasses. But during those 4 minutes of totality, even without the solar eclipse glasses, you can still see some really cool effects. So you can see shadow bands leading up to totality. When that last sliver of sunlight passes through the Earth's atmosphere and gets refracted onto the ground on Earth's surface, you can see these wavy bands of shadow either on the walls on Earth or on the ground. You can also see this beautiful diamond ring effect in Baily's beads as the light from the sun passes through the valleys, the craters, and the mountains of the moon in the foreground. And that's those little shiny little white spots shown in the image. You can also feel the temperature drop as the sun's rays are completely blocked out by the moon. And during totality, you can see the sun's corona, that wisp of diffuse plasma bordering all the way around the sun that we usually can't see, not during a total eclipse. We can also see a little sliver of the chromosphere, which will be faint and red during the total solar eclipse. But remember, this is only for those 4 minutes of totality that you can take off your glasses. So set a timer to be safe. Make sure you don't look at the eclipse during partiality. And finally, during the total solar eclipse, we can also see constellations behind the sun in the daytime sky, which we usually can't see. There's actually a very cool experiment you can do to verify Einstein's theory of general relativity using the light bending of these constellations seen around the sun. You can ask questions about that later on. I'm not going to go into depth here, but you can also look up the Eddington exhibition. It's a very fun story in the history of astronomy. So I have tried to hammer home the point that these total solar eclipses are super special, super amazing events. The next total solar eclipse passing through the contiguous United States won't be until August 2044. And even then, the path of totality is only going to graze the northern end of the United States, going through maybe North Dakota and and it's mostly going to be in Canada. So you will have to wait until really August 2045 to see the next total solar eclipse through the contiguous United States. It's going to go through central California, dip down, go through Texas once again. The next lunar eclipse is going to be in the US in March 2025, but it's not going to be as impressive as a solar eclipse. So I hope all of you will be inspired by this to step outside on April 8th and try to catch a glimpse of the moon covering part or all of the sun. And hopefully you'll be using your eclipse glasses so that you don't damage your retina. But I think we have a minute or two for a few questions about the eclipse before we move on to some more trivia about black hole paleontology and eventually Flora's talk. Otherwise, if you want to wait until the end, we're happy to answer questions after the talk and after the Q&A. Yeah?
Hi, not to have it non-tangential, but the observatory upstairs, I remember every once in a while when you had public lectures, you would be able to go up there sometimes, and I remember
Yeah.
during COVID, I think is when it stopped.
Mhm.
I'm just wondering, are there any plans to open it up again? And then back to regular questions again.
Yeah.
That's been on my mind for like a couple of years.
That is an excellent question. So we currently can't bring a lot of people up to the roof because there is significant water damage on the roof. The telescope is working fine, but the roof is just structurally unsound. This has been the case for a little bit. We've been waiting for Columbia Facilities to come and fix it. As I said last time, we're not suggesting necessarily that you send angry emails to the Columbia administration, but if you do want to expedite this process, it wouldn't hurt to send these emails.
Great, so we'll
As-
send about a couple hundred angry emails.
Yeah. We, we would love to have more events on the roof, but currently it's just not safe for them. I'll leave it to you to do your own research to find those emails. But, okay, if there are no more questions now, we'll move on to the main event. So we're going to start with some trivia related to black hole paleontology, which actually William Groger is going to read. Then I'm going to introduce our keynote speaker, Dr. Flora Broekgaarden, who's going to give a fantastic talk on her research. So for now, I'm going to transfer this over to William.
We're gonna do this a little bit faster than trivia normally, just because we had the solar eclipse trivia before. Okay, question 1. The final stage of a star's life cycle vary depending on the star's initial mass, with initially lighter stars dying out in distinctly different ways than heavier stars. How massive does a star need to be initially for it to end its life as a supernova, leaving behind a black hole or a neutron star? We have option A, at least the mass of our sun. Option B, at least 4 times more massive than our sun. Option C, at least 8 times more massive than our sun. Or option D, at least 16 times more massive than our sun.
Tough question.
I'll give you a few seconds to think it over. Okay, show of hands for option A. Option B. Option C. Or option D. It seemed like most people picked option C, and that is correct. Question 2. Many of the chemical elements necessary for human life originate in the cores of massive stars. Which of the following elements is not primarily sourced from massive stars? We have option A, carbon, option B, oxygen, option C, silicon, or option D, potassium. Again, I'll give you a few seconds to think it over.
Trick question.
Okay, show of hands for option A, option B, option C, or option D. Okay, most people picked potassium. It was actually carbon, which, you know, a couple of people got
This
it.
is such a
but-
trick question. It's a good question.
Yeah.
No, I agree, but
Okay. Question 3. The quantity known as the Schwarzschild radius marks a critical threshold for a black hole when all the mass of an object is compressed within a sphere with radius equal to the object's Schwarzschild radius. Light can no longer escape from the surface of the object. To what radius would we have to compress our sun to create a black hole? We have option A, 3 meters, option B, 3 kilometers, option 300 kilometers, or option D, 30,000 kilometers. Okay, let's see a show of hands for option A, option B, option C, or option D. All right. It was B. I think a lot more of you got it than the previous question. So, okay. Question 4. When two black holes coalesce, they release gravitational waves or ripples in spacetime. The first such detection of these ripples occurred on September 14th, 2015. Roughly how large were these detected ripples on Earth? Option A, the diameter of a golf ball. Option B, the diameter of a dime. Option C, the diameter of an atomic nucleus. Or option D, 10,000 times smaller than the diameter of an atomic nucleus. All right, all of these are pretty small, but let's see. Show of hands for option A, option B, option C, and option D. All right, some of you got it correct. It is option D. It is incredibly small. And question 5, which I think is the last one. Over the past decade, the Laser Interferometric Gravitational Wave Observatory, or LIGO, has provided a wealth of information on black holes and compact stars through the detection of gravitational waves. Which of the following images depicts LIGO?
Nice.
I'm not going to read off anything for these. Okay, who thinks option A is LIGO? How about option B? Option C? And option D? Okay, I think most of you got it correct. It is option B. All right.
This is a tough question.
Okay. So, thank you so much to William for leading the trivia. Another round of applause for William. Okay, so it's now my honor to introduce our main speaker, Dr. Floor Broekgaarden. It was actually very difficult putting together an introduction for Floor because her CV is so extensive, so impressive. It was hard to choose what the most important parts were to put in the introduction for Floor. So I did have to cut down the CV a little bit, but hopefully it still does Dr. Floor Broekgaarden justice. So Dr. Broekgaarden is a junior fellow in the Simon Society of Fellows, a position that she's pursuing currently in New York City at Columbia University at the Center for Computational Astrophysics and at the Simons Foundation down in Midtown Manhattan. She's also currently a research professor in the Department of Physics and Astronomy at Johns Hopkins University, where she'll start as a full-time assistant professor by July 2025. So very exciting for Floor, but very sad for us here at Columbia. She also spends part of her time in Tucson, Arizona as a visitor at the Steward Observatory.
Yep.
So she's really doing astronomy all over the U.S. And so since her time as a grad student at Harvard University and at the Harvard-Smithsonian Center for Astrophysics, Dr. Broekgaarden's research has focused on gravitational wave or black hole paleontology, which we'll talk about in just a little bit. So for her research, she studies massive stars from their remnants as compact object coalescences. And she's pursued this problem from a myriad angles, really every angle you can to study massive stars and gravitational waves. She's looked at massive stars, binaries, black holes and neutron stars, stellar evolution, pulsars, astrostatistics, artificial intelligence, machine learning, double contact object merger rates and properties, and population synthesis models. So a whole lot of research. And to help with this, she has joined and formed a number of collaborations. So one recent collaboration she's the current co-PI of is Astro AI, which is a new and growing initiative to accelerate artificial intelligence in astronomy at the Harvard Center for Astrophysics. So a lot of impressive research work. And even beyond her research, Dr. Broekgaarden has done some incredible work towards improving the astronomy community as a whole, including initiating a group to support early career astronomers, leading a conference session of the European Astronomical Society for early career astronomers and their supporters, and creating support resources for combating workplace instability in astronomy. And actually, earlier today at noon, she gave another talk on imposter syndrome and DEI in astronomy. So hopefully she's not too exhausted tonight. In her free time, Dr. Broekgaarden does love hiking, running, playing volleyball, cycling, and juggling, which I think we'll see tonight. So without further ado, I'm extremely happy to welcome Dr. Floor Broekgaarden.
That's so many words. Thank you. That's a lot of words. Thanks. Yeah, good night, everyone. Good evening, I should say. Welcome. Thank you for coming to this lecture. So you can just call me Floor. I'm an astronomer here at Columbia. And today I actually want to tell you the story. Let me just turn off the caption.
It's extended.
Oh, I see. Okay. So today I actually want to tell you a story. And for me, the story is about how, for me, massive stars are the dinosaurs of our universe. And this is because, similarly to how paleontologists study fossils to actually study and learn about the lives of dinosaurs and how they formed, lived, and eventually died, I study the fossils of these massive stars, black holes, through gravitational waves, to understand how these massive stars once upon a time formed, lived, and died. That's a lot of words, but we have some time to unwrap that. So let us do that. Compared to our sun, shown here in yellow, the massive stars that I'm talking about are these stars that are at least 10 to 200 times the mass and size of our sun. They're extremely rare. So these massive stars, only 1 in 1,000 stars is actually born as a massive star. In addition, they're kind of like the rock stars of our universe because they live very fast and die young. And so typically the lifetime of a massive star is only 1,000 times shorter than the life of our own sun. And so combined with these two, it means that it's extremely challenging to find populations of these massive stars. They're extremely rare among the stars. And so it's really difficult for people like me who like to study the lives of these massive stars to actually find them and do detailed observations of many of them. And this is true for our own Milky Way, where we often rely on very expensive surveys and can only study a few stars. But it's even more true for when we want to study these massive stars in other environments, such as galaxies much more further away from us. And so very little is actually known about these massive stars to date. But there's one thing that we do know about them, and that is that they play an extremely key role in our universe by all these different processes. So, for example, they actually form new stars, they trigger new star formation. They go through these like super high energetic phenomena, like these transients and supernova, and can leave behind a neutron star and a black hole. But more importantly, as you already saw in the quiz, they actually produce a lot of the elements that we see here on Earth. So for example, they produce all the oxygen that we breathe here on Earth today. All comes from these massive stars. And to show you that, here's actually a diagram that shows, for the table of elements, here's hydrogen, helium, and then it goes up in elements, where all these elements are coming from. And here in orange are all the elements that come from massive stars and are only produced in massive stars. And so you see oxygen is right here. All the oxygen is formed in massive stars. And so this is because only these massive stars are hot enough in their cores to actually go all the way and produce oxygen, these heavier elements. And then when they explode, they throw out all this oxygen into the universe that then just spreads out, can collapse again to form new stars such as our own sun, and also to form planets like the Earth. And that's how it eventually ends up in our own bodies and in our own Earth and planets. And so actually, if you look at your body mass and what it's made of, most of our body mass, so our weight in body, is actually coming from oxygen, for instance, from the water. So it is about 73%. And so for 73%, we actually are made of these massive stars that exploded. And so you might be familiar with a famous quote that says, "We are all made of star stuff." Well, I hope after this lecture, you go home with a new quote that I would like to add, which is, "We're actually made of mostly massive star stuff." To just emphasize how important they are. But okay. There's something else that's really cool about these massive stars. And the most fun way that I always like to share this is actually by showing this famous constellation. So do people know what constellation this is? You can shout. Orion. Yes, so this is Orion. And it actually has like many very bright stars. Here are some of their names, including Betelgeuse, and then you see all these blue stars. But now I also have a trivia question for you that luckily wasn't mentioned yet. If I'd ask you, okay, out of all these stars, if you were to count, how many massive stars are in this constellation? What do you think? Six? Yeah. So it's actually a really difficult question because it turns out, you see about 8 stars. And actually all 8 of these are massive stars. That's also why they look so blue. Betelgeuse is a special massive star. This is a massive star that's actually at the end of its life, and so it has kind of already blown up and is almost about to explode. Almost meaning several million years. And so that's like why it looks a bit red, but it's actually also a very massive star. But the actual answer is not even 8. It's actually at least 12. So where are they? Well, it turns out the coolest thing, or the thing that I think is the coolest about these massive stars, is that compared to our sun, these actually often live in pairs, where there's another star that's orbiting around them. And so if we go back to this picture, it actually turns out that, for instance, some of these stars, these light points, are actually 2 stars, 2 massive stars orbiting around each other. And there's actually one that's at least 3. And now you would be surprised, like, okay, I thought you said massive stars are rare. Well, they are rare, but these stars are really far away. But these massive stars are so bright that we can actually still see them with the naked eye. But they're so far away that it's really difficult to even study these very bright stars. And so actually, for instance, with this one, which is 3 stars, we think there's more, that there's even like another pair of 2 stars like orbiting these 3. But we're not 100% sure how many companions they have because they're so far away and it's so difficult to study them. And so we really need other means to study them. But when you have a pair of stars, it actually turns out that the life of a star in a pair is very different from that of a single star, maybe just like here on Earth. They can actually like orbit around each other, they can exchange mass. And these massive stars, when they end their lives, they explode and go supernova, and eventually leave behind a black hole. And so when your first star in the pair explodes and forms a black hole, if the pair survives, which is actually really challenging, the other star can also explode and form a black hole. And what you might end up with is a pair of black holes, which is really cool. Now, I'm going to visualize that with marbles that you see here. And so when you have a pair of these 2 black holes, they can actually slowly spiral in over many billions of years until they eventually collide and form a slightly more black hole. Now, something very special happened. In 2015, scientists for the first time ever saw such a collision of 2 black holes colliding through gravitational waves. And this made people like me wonder, hey, if we can observe these collisions of black holes, these fossils, can we use them as fossils to study how these massive stars once upon a time formed, lived, and died? Just like how a paleontologist would study fossils to try to learn how dinosaurs once lived and eventually died. Okay, And so this is what I have become to call black hole paleontology, or sometimes gravitational wave paleontology, using these black hole fossils to understand how these massive stars once formed, lived, and died. Okay, so how do we actually detect these black hole collisions? And what are these gravitational waves that I've been mentioning? Okay, let's start here. So all around us, there are these pairs of black holes that eventually collide. And when they do, they form these ripples in space-time itself, these waves, that can travel through space, and actually were once predicted by Einstein, and after millions of years can reach us here on Earth, where they actually squeeze and wiggle the Earth itself. This is vastly exaggerated. It's very tiny, it's like less than an atom size. But here on Earth, we can detect these super tiny wiggles with these laser interferometers called LIGO, the ones that you already saw in the quiz, that can actually detect these tiny deviations in space-time itself. And with these laser interferometers, what we actually observe is a signal that looks something like this. This is a real signal. And this is what we call a chirp, because if you were to listen to this signal, it sounds something like whoop, whoop, as it goes up in frequency. And from these wiggles, we can actually infer the properties of the black hole collision. So we can infer things as the masses of the black holes. We can infer how often they collide, and for instance, what their mass ratio or even spins are, which we then hope to use to learn about these massive stars. Now, there's one really cool thing about these massive stars and how they form black hole collisions that makes them really cool for studying stars, not just here, locally, close to us in our own Milky Way, but actually all across our universe. And for that, we have to kind of look at okay, what do I mean? How does the universe work? This is probably a picture that you might have seen before that shows the whole evolution of the universe. So the Big Bang and this beginning of the universe starts here, when the universe expanded. First star formation happens around here after 400 million years, and then today we're about here. So today our universe is about 15 billion years old, and we live kind of in this side of the universe. But I always like to think a little bit about it as okay, what would that look like in a year? So if we scale down the entire age of the universe, so how old the universe is, to a calendar year, so 14 billion years becomes one calendar year, then the universe evolution kind of looks like this. So this is the timeline where you have all the different months. So here is December, and then all the way here is January. So you have the universe is born. The first stars actually formed the very first month. And then you have stars forming. The Milky Way was formed around here. So only in May, almost halfway in the year in. The sun was actually only formed in September. So it's only 3-4 months old, very young. And the Earth as well. And then you have all this life and other processes. But we can actually zoom in. So let's zoom in on just the last month in this universe time scale. And what you find is actually, again, that only in the last, you have all these different processes. The dinosaurs were only on the 25th day, so Christmas Day of December. And us humans actually only started to exist on the final day in this calendar year. So one day before midnight on December. And you can zoom in even more. If you just zoom in into the last minute, then there's actually civilization. Columbus is born and arrives, and eventually, only in the last, very last second, you have things like the scientific revolution, industrial revolution, and then all the wars, and we are here today. So the universe is pretty old compared to a human being, and even compared to how old the Earth is or our sun is. It's pretty old. And so scientists like myself are really curious to understand how the universe came to be, how oxygen, for instance, was spread throughout the universe, and how these stars lived throughout time, not only recently, but also a really long time ago. Okay, and so what makes these black hole collisions special is that actually stars might maybe form a pair of black holes really early on in the universe, but it can actually take many billions and billions of years until they eventually collide. And so this is cool because it also means that the black hole collisions that we see today with these gravitational waves actually might inform us about and probe how stars lived in the distant past, all the way until this first star formation, so this very first month of our universe in this timeline. But this also makes it so much more challenging to actually do the thing that I want to do, which is use these black hole collisions to understand the stars, because the black hole collisions themselves don't directly probe the stars themselves. So you can kind of compare, like how maybe when you see a fossil, you cannot directly tell whether the dinosaur had feathers, but you have to like kind of model like dinosaurs with and without feathers and see what kind of fossils they leave behind. And so it's the same here. When we see a black hole collision, we cannot immediately tell which one are the stars, when did they form, when were they born, so what do we learn? And to demonstrate that, because this is such an important point, I actually wanted to do a little bit of an experiment with you all, where you actually get the opportunity, or at least some of you, to be part of my simulation in this talk. And so what I have here is I have a timeline, which is the same timeline that starts here at the beginning of the universe, when the universe was 0 years old. And it goes all the way after 12 months to today. So today is like here, where the universe is 14 billion years old. And I now would like to invite 15 or 20 people, volunteers, who maybe want to come and be a pair of stars for tonight. So please, 15 or 20 volunteers, come with me, and I'll give you a sheet of paper. And that sheet of paper will have a sentence that says, I'm a pair of stars that was formed in the universe when the universe was this old, and 6. And the 6 means the 6 here. And if I give it to you, I'd like to ask if the volunteer will try to like stand in front of the number that's on the paper and hold the paper like this. So please come forward, 20. Yeah, you can come together if you want as well, that's fine. There you go. So try to find your place of birth. Thank you. Yeah, thank you. Come on, Anna. Come on. I need a few more volunteers. Oh, just the front. Yeah, that's for later. Yeah, just so you need to stand with the 14. Few more volunteers, come on. Thank you. Few more, anyone? Yes, thank you. Thank you, sir. Okay. And if you have the same number, try to like stand close to each other, or like if maybe some people can be like in front of each other. And if you are at the birthplace that you were born, please hold the sign with that number that you were born in front of you so that the rest can see it. Only with the number, yes. Okay, this is great, this is great. Okay, so all of these lovely volunteers tonight are, each one of them is one pair of massive stars that's born in this universe. But can you see something special about maybe the distribution of my pairs of stars? What do you see? A lot of 4s? Yeah. So if I go like early in the universe, my stars are a bit lonely. There's only like 1 at 2 and 1 at 3. Sorry. And here, what about here on the far right? Only 1? Also very lonely. Oh. And this is actually true for the real universe. So if you were to plot, and people do this, and try to observe how many stars and pairs of stars are formed as a function of time over the universe, we actually find something like this. We find that early in the universe was still too hot to actually form many stars, and you don't form that many stars, so you kind of have to build up. Then you form a lot of stars because each of these stars explode, and that triggers new star formation. So around 4 gigayears, or like 4 billion years or 3 billion years, that's when you form most stars. But then at some point, actually, the gas in galaxies is kind of, they fuel out of like most of the gas, and so you actually don't form as many stars anymore as you do before, and that's like why it goes down, because your galaxy is kind of out of gas to form new stars. So that's true. Okay, great so far. And that's actually what, this kind of forms what we call in astronomy a star formation rate that follows this function. It's a very commonly used function. Now, okay, you were all born as a pair of massive stars in this simulation of mine, but not all pairs of massive stars make a pair of black holes, unfortunately. What can happen is that you maybe start with a pair of stars, but when one goes supernova, it might actually disrupt and break up the pair of stars. Just like how maybe many relationships on Earth break up, especially among the rock stars. So if you want, you can turn around your thing, and it will actually show you a check mark if you became a pair of black holes, and a cross if you didn't become a pair of black holes and you broke off. What do you see? What do you see? Where are the pairs of black holes versus? Use your scientific analysis, data analysis technique, some AI. What do we see? What do we see? Any relationship with where the check marks are? Both ends? Yeah, so like on the far right, there's a lot of crosses, right? And there's kind of like check marks here and then some crosses here. So this is, again, something we actually see from the simulations that I do. I mean, it's almost a real result. But like we find that like some stars, especially the stars early in the universe, are very good and successful in making, like staying together and forming pairs of black holes. But maybe the stars that more formed today, so closer to when the sun was formed, they're actually not so good at forming pairs of black holes, and they most of the time break up. And it's something interesting that we try to understand. Okay, everyone who didn't become a pair of black holes can go back to their seats. You can keep your sheet if you want. The rest should stay, yeah. Okay, now comes the most important part of the simulation, which is that, okay, all of these stars, they formed a pair of black holes, so we're happy. But as I said, these black holes, they actually can take really long time before they collide. So what happens is that maybe the pair of black holes formed here, but they actually take many, many gigayears to collide and might only collide much closer to today. So on your sheet, I actually calculated with my simulation how long for each one of you as a pair of black holes your time is to inspiral. And so you can see it has a number underneath the check mark that says when you collide. And I will ask you to move to your collision location. Yeah, at 12. You need to be at 12. Yes, perfect. See some very like, oh, what am I still doing here? Regrets, faces of regret. No. Okay, what do we see? It's interesting, right? So like all of them collided much closer to today, right? So you can imagine if I'm LIGO and I'm here at today at 14 gigayears of our universe, and I'm staring into the universe, that I actually probe and maybe detect all these collisions. Well, this one, yeah, I could see definitely, and maybe I can only see until here. So some of the collisions I might not see yet because I'm not sensitive enough, but I might actually see a lot of collisions. Now, can you flip over your card and show me where you were formed? Yes. So you already see that actually, like, you see there's like a lot of 4s and then some 6s. So it's already a mixture, and these are basically the times at which these stars were formed. So even though I'm observing very late times, like maybe only until like 12 gigayears that the universe was old, I can actually already see stars that were formed much earlier in our universe. And so this is why these black hole collisions, when I see them today, they might actually probe these stars that were formed much, much earlier, like maybe in February or March or April in our universe. Okay, a round of applause, and you can go back to your seats. Let's see where we were. Okay, so that's great. But this mixture, and that there's so many different things that can happen, and so the observations that we do don't directly tell me, but which star am I dealing with? Like, how do I know where they were formed, how they were formed, how long it took them to reach here? So this we don't know. So in practice, when we see a black hole collision, it's really challenging for us astronomers to directly go back to this picture of like how, like what were the stars look like, how did the stars live? Just like in paleontology, it's hard to like tell feathers. And so instead what we do in practice is we have to kind of forward model populations of stars, and with simulations like see, okay, if I start with all these stars that form over time, with my theory or model, how do they evolve? What do their black hole collisions look like? And when do they merge? How often do they collide? And I can compare that to observations to actually test these theories and learn something. And so that's what we do in practice. Now it turns out that this is actually challenging because of three main challenges in this field that make this so difficult to do and properly do this forward modeling. And that's exactly where I and my research group are trying to improve on. So we're trying to basically overcome all these barriers in order to truly do this black hole paleontology. But at the moment, the honest answer would be is that our field sometimes looks a little bit like this. Where you're trying to run over some of these hurdles, but it's so challenging. So at the moment, there's no scientist gravitational wave or black hole paleontologist scientists that truly can do this and can do this forward mapping and just truly learn about these massive stars. Okay, so in the last part, I just wanted to briefly highlight a few of the things that we do in my research group to try to overcome and understand some of these hurdles, overcome them, and hopefully go to a better place. Okay, so the first thing let's focus on is this big hurdle is that we're actually not entirely sure how these black holes actually formed. And so that's the first hurdle that I'm attacking. And it actually turns out that if you have theorists like myself, we like to come up with many theories of how you can form colliding black holes in our universe. And there's basically this whole range of formation channels. And you can kind of compare it with how there's maybe different dinosaurs that lived, and you're trying to figure out if you find some bone or some head, okay, which of these dinosaurs is it? So let me just explain to you kind of the two main channels. So the first channel is on the left that we call in the field. But it basically consists of okay, you start with two of these massive stars that were already born in a pair. And then you have this process where, okay, maybe they can transfer some mass. One explodes, forms a black hole. The other one explodes, forms a black hole. And only if they survive all these phases, they can form a pair of black holes and then collide. So that's all these left channels are kind of that same order. Now, we also have these other channels, which are these dynamical channels. So here's something else happens. Here you have a big, dense ball or a cluster of stars. And these stars, they form black holes, and the black holes kind of sink to the center of these balls of stars. And in these centers, they can actually undergo three body interactions. And usually what happens is that the least massive black hole actually gets kicked out, and you end up with two black holes that can eventually collide and form the black hole pair. So that's kind of the second channels. There's always some kind of interaction, juggling going on between other stars and black holes, which you have to learn if you're in my group eventually. And it's really useful. So that are kind of the two channels. And so one of the things that I and my collaborators have developed are actually some kind of factories or tools that can then model the evolution of these stars for these different theories. So you can really see it as that there's some factory that takes in hypothetical pairs of stars with, for instance, different masses, and then calculates whether that pair of stars forms a pair of black holes successfully. And so here you can see that a white cross means no pair of black holes, but then every now and then you try to write masses and it actually forms a pair of black holes. It forms a stellar pair that can stay together and form one of these collisions. And actually one of the students that's here, Anna, who's in the audience, showed that, for instance, when you do it, it turns out it's actually really, really difficult to form pairs of black holes. And that you maybe start with a lot of pairs of stars, but then you kind of have to survive all these phases. Okay, you have to survive the supernova and not disrupt and break up during that first phase. Then you have a second supernova, and you should also not disrupt during that phase. And so that it really, if you start with all these pairs of stars, only a very few might actually reach this final stage that's here, where you can actually form a pair of black holes and collide. And so in practice, when we do these simulations, we really find that only one in maybe every million pairs of stars that we try with different masses really form such a pair of black holes, because they're just so challenging to study them and to form them. But I kind of like to think about it as okay, if we somehow figure out which stars can do this, then we kind of find the recipe for the longest lasting marriage in the universe. So firstly, it's kind of oh, you can kind of see yourself as a relationship therapist for the stars. Working on that too as a second career, but maybe later. So this is something that we're doing, and we're really trying to do the same process for all these different theories and information channels to kind of get a picture of how often do you survive and how often do you make these black hole collisions. Now, The second thing that's actually very related to this that my group is working on is actually this question of like, but which stars exactly can form these pairs of black holes? So what relationships, like how do you need to start with? What kind of stars do you need to have to actually be that 1 in a million successful one that can survive? And it turns out that this is actually a really, really difficult question. And it requires a lot of machine learning. Because it turns out that you don't just try different masses of stars, but these stars have actually many different properties. And so you're kind of not working in these like 2 axes, but these many, many axes, such as, you can start with a pair of stars that's further away from each other or closer to each other, that is on a very eccentric orbit with each other, so on and so on. And so in real life, you're not just asking, okay, which masses do I need to start with, but like really in 10 dimensions or 20 dimensions, what are the properties of stars that are successful? And so one of the things I worked on with also students is to make this more efficient. So we came up with an algorithm, a machine learning algorithm. People nowadays would call it AI, that we call it stroopwafel, which is my favorite cookie. I'm from the Netherlands, so that's why. And it sounds very, very complicated, but I always like to simplify it by saying it's really, really similar to playing the game Battleships. Do you know it? So this is basically a game where you start out with a grid, and you're trying to guess the locations of the opponent's ships. And so how you would play is, like say I played against Anna, one of my students, is that I would be like guessing F6, and then she's like hit or miss. And the goal is to find the opponent's ships faster than that they find your ships. Now, in principle, so this is kind of a 2D version of that, in principle you could do this completely random. You could just like each time that you guess, just make a completely random guess in that grid. Not only would this be a very boring game of battleships, because it's like, okay, you could just like roll dice and then find your next guess. It actually turns out that this is not a very good strategy. And so I bet that how most of you play it is that instead you do kind of what the strategy that's on the right, where you maybe start out random guessing these different points, but then once you have a hit, which you'll see as like a red cross here, instead of just randomly continuing, you kind of like search around it. Because you kind of know like, okay, the rest of the boat needs to be somewhere there. And this is actually, I did the actual like calculation, mathematical derivation of like, okay, how long does it take to win a game of battleships? No one wants to play battleships with me anymore. But it turns out that you can like, on average, finish the game and win the game in 65 tries with this strategy, where like the normal strategy takes about 97 guesses. So whenever you play this, you will almost always like win, like 99.9% of times you will win with this strategy. So we do something very similar for our simulations. But now instead of trying to guess the location of these ships in your opponent's like grid, in our case, we're actually interested in the locations or like the properties of these hypothetical masses that you should try. So it's just their masses, like what's the mass of this one star and the other star, such that if you try these masses of stars through this factory, that it makes a pair of black holes, which are here these like islands. And so a hit would be like a pair of stars that is successful, can stay together, and forms this like long-lasting relationship. Now it's a little bit more complicated, but we basically apply the exact same strategy as this battleship game, where before simulations were always kind of like randomly exploring this space, and now we wrote like a machine learning algorithm that basically does the same as battleships game. It's a bit more complicated because there's some things that are complicated because like, for instance, you have these islands that don't look like perfect boats, and you don't actually know beforehand like how many of these are going to be in your simulation or in your theory. And the other thing is that you're actually playing in these like 10 or 20 dimensions. So like imagine trying to do the same strategy with like a 20-dimensional battleships game. Becomes a little bit more challenging. But the good news is we did this, and we actually managed to make these simulations like 100 times faster by using this battleships game tactic. And so that might not sound like a lot, but it's a lot. So it means that like a simulation that otherwise takes like 400 days to complete or like a year, now can be completed in just a few days. And so that's a huge improvement for astronomers like me that don't like to wait for an entire year to then find a bug in my code. And so with this strategy, me and like my students, we actually for the first time can really try to say, okay, what are these properties of stars that make them successful in making a long-lasting relationship and a pair of black holes that we hope to use. Okay, last but not least, and another thing that's very important is that actually we need to understand and learn like where do stars form in our universe, and also where do they collide? So in this experiment that we were playing, like, do they collide here, or do most of them collide further away? And so I also have a lot of students working on that, and especially Adam, who is also from New York here, showed recently that surprisingly, when, for instance, you look at one of these theories, that even though there's a lot of like different answers for like, okay, how many are colliding today, this is early in the universe, even though they kind of disagree about how many are colliding today, that they have very similar behavior for what they predict as a function of the age of the universe. And so this is nice because one of the things that we're finding now is that these different theories or formation channels, so these are kind of these, do they form in a cluster or form from pairs of stars, might actually leave very different imprints in this like space. If you look at like how often are they colliding as a function of time. And so this might actually provide us great hints that if we see observations and we see how many black holes are colliding as a function of our universe age, which we will eventually do, we might actually tell apart how they were formed and answer these questions like, how do most of the black hole collisions that we see today, how were they actually formed, and how did they once live as stars, which I'm very excited about to answer. And I hope we will find an answer in the next 5 years. Yeah, so all in all, with my group, we're really hoping to tackle all these barriers. And these were just samples, but they were kind of working on very many different projects and different like challenges that like arise in this field. But we're really hoping that we can kind of help go from this left picture, where we are today, to this right picture, where we like kind of understand these challenges, have learned to overcome them, and are now kind of like just like running like through the track, maybe getting some Olympic medals in Paris, I don't know. But I think that would be really great, and I think it would really help us like answer some of these big open questions in astronomy. And it couldn't be at a better timing because, as I told you, in 2015 we observed the first pair of black hole collisions through gravitational waves, and we actually observed kind of 3. Already in 2017, so just 2 years later, we updated this, had a new observing run, more detections, and now had 10. And then in 2020, in the last run that has been made publicly available, we now have found about 100 of these black hole collisions. So this is really rapidly increasing. But most excitingly is actually that the US is leading some of the newest and best observatories, one called Cosmic Explorer. That's kind of a big update to LIGO that we have today. And so the hope is really that in the future, we're going to see like millions of these black hole collisions per year. And we're actually, like with the detector that we're building, we're hoping to find every single black hole collision every year that's colliding in our entire universe. Not just in December, which are the ones that we see today, but all the way until like January, and these very first black hole collisions. And we're hoping to use all these observations to really see, do these black holes look differently as a function of time? And so does it mean that stars, for instance, formed, lived, and died differently as a function of the age of our universe? Ultimately, we hope that by all the work that we do, we can really do this forward modeling and help use these observations to like map back to how these stars once formed, lived, and died, so that we eventually can complete this picture and really do black hole paleontology, so we can use these black hole collisions to truly learn about these mysterious massive stars and their pairs and their relationships, to eventually truly understand many of the processes that they rely for, and answer some of these like biggest open questions today, such as how do these black hole collisions form? How did the oxygen that we breathe today get distributed throughout our universe? And how do these stars form, live, and die? And so with that, I'll say thank you and open it for questions.
Okay, thank you so much. That was a fantastic talk. Another round of applause for Dr. Okay, so a few things. First, okay, so we're going to do about 15 minutes of Q&A with Floor. So we're also going to be raffling off 3 pieces of Columbia merchandise throughout the Q&A. In order to be eligible for the raffle, you need to fill out the check-in form. So that's tinyurl.com/astro-check. in. Also, we have, so you can ask your questions in person, raising your hands. If you want to submit questions anonymously, there is a Google form for this, tinyurl.com/astro-questions-mar22 for March 22. Actually, earlier today, Flora recommended an alternative to this anonymous question asking service. So we're going to actually implement that at our next talk, and it looks much better than what we currently do. The last announcement, unfortunately, it is too cloudy tonight for stargazing, even the moon is covered by clouds. But over the next 2 weeks, to hype up the solar eclipse on April 8th, we will be doing some daytime observing. So if we have some sunny days, hopefully warm spring days, we're going to take a solar telescope out to the low steppes to look at the sun. So even though we can't do observing or stargazing tonight, we'll be able to do sun gazing, hopefully, in the next few weeks. So, yeah, without further ado, if you have any questions for actually, I do another. Thanks.
Run.
There you go. The handheld.
I can also use this, I guess.
I turned on the handheld, so it should be.
No, low battery.
You can do this, maybe.
Yeah.
Great talk. My question is, you showed that the birth of the stars, the massive stars, follows something a bit like a log normal distribution. Does that mean eventually one day they'll run out? And does that have any implications for the universe?
Oh, yeah, no, that's a really good question. And yeah, it is true. So like we're currently running out on like forming new stars. So compared to early in the universe, we form way fewer stars than we used to be. And so there are like a lot of theories how like once a very long time, like at some point our universe will get dark again, that like all stars are done shining and have either become white dwarfs or neutron stars or black holes, and no new stars are formed, and so you just end up with like a dark universe. Yeah, so it's very interesting, but very long time from now. Like we'll probably not notice that.
So you
Yeah.
need to speed up your work.
Yeah. I think there's also a question. Yeah.
So I have a question. So can you also do like say neutron star paleontology or white dwarf paleontology, or is it just black holes?
Yeah. No, that's a really good question. So currently, with the current detectors, we can see neutron stars and neutron stars and black holes and two pairs of black holes. No white dwarfs yet. And actually, the neutron star black holes are my secret favorites of those three. So I was actually said I had to like reduce them. I usually have a slide because one of the cool things is that actually some of the work that I did was showing that like, hey, these might be more common than most scientists today expected. And everyone is telling me like, no, we're never going to see them. So much so that I organized a meeting called Where Are the Black Hole Neutron Stars? Because we hadn't observed them yet, and everyone was like, yeah, obviously. But I was like, no, I think this is a surprise. And then, I'm not kidding, the day before my meeting was held, which was planned for a year, everyone had like been preparing talks for a year. The day before the meeting was held, the first observation of a black hole neutron star was discovered, so everyone had to change their slides. It was like the fastest outdated like conference talk because the first person who presented like showed up my poster that said like, where are the black hole neutron stars? Here are the black hole neutron. So yes, you can do it. I love those, and it's very useful also to kind of like see. We think slightly less massive stars make these neutron stars, so it actually tells us about different ranges of masses. And in the future, there's going to be a space-based gravitational wave detector, also partly led by US and Europe. And those are actually going to detect all these white dwarfs. So that will tell us a lot about these other paleontology things. So yes, absolutely. And people should start calling it neutron star paleontology. I love that. Sorry, long answer.
You can use the podium mic over
Oh,
there, and I can
yeah,
go
that's
around
smart.
here.
That's so smart.
Okay. Yeah, question here?
Okay, so I'll read questions from the Google form. So how do you confirm or validate your simulations?
Oh, good question. Does this work or no? Okay, otherwise I'll just scream. That's a really good question, and It's actually a question that, as scientists, we're kind of asking every day, like, how do I make sure that the simulations that we do make sense, or like, what are we learning from these simulations? And so, for me personally, it's like, when I do these simulations, I don't only make, in the rare cases, these pairs of black holes, but we actually also make all these other things, like these stars that disrupt. And so we actually have also some observations of like stars that are flying through the universe. We call these like runaway stars that are like running away from their breakup. And so you can actually also compare your simulations to like all these other observations. And if we truly understand and do the simulations well, it should kind of explain all these different phenomena that we're seeing with different telescopes. So that's the main way that we're trying to verify them. But it's a big problem, yeah.
Okay, my short question is, how do you distinguish between a collision of a pair of black holes and a black hole neutron star collision? Is it simply the mass, or is there something else? And just relatedly, a larger question is, I'm just wondering what information the gravitational waves give you. My understanding is that you can tell how far away they are from the amplitude, you can tell the masses from the shape of the wave. I mean, what else? Like the spins of the individual stars, and what can't you tell that you would like to be able to tell?
Yeah, that's a really good question. And so it's actually it's somewhat difficult to tell a black hole neutron star and a pair of black hole colliding apart. But one thing from the observations, you usually get the masses and you get like some estimate of the distance. And so you can imagine that, like, okay, for instance, if you look at like how big the gravitational wave is when you reach it here on Earth, that's going to be smaller in amplitude, or the signal is going to be smaller either when the black holes are further away, or if they're less massive, and so they make less of a wave when they collide. And so we actually get kind of two independent observations of these. We can namely measure like the amplitude, but also this change in frequency actually gives us directly the masses. And then if we know the masses, we can actually, from the amplitude, estimate the distance. And so that combined gives you some like fairly precise estimate of the individual masses. And then people go and say, for instance, if something is more massive than 3 times the mass of the sun, we think it cannot be a neutron star because we think neutron stars are smaller in mass. But this is still an open question, and I actually hope that's one of the things we will learn in the next 5 years.
But you do get an absolute estimate of the distance simply from the shape of the wave.
The shape of the wave, or the amplitude together with the mass. So if you invert, you get the mass from the shape of the wave, and then from the amplitude and the mass, you get the distance. Yes. So
Okay,
we're
but
also using it, like we're trying to use it for like measuring the Hubble constant and like the expansion of the universe as a distant measure.
but not the spin of the black holes.
You do get that, but not so precise. Yeah, but a little bit. Yeah.
Another question?
So how do the moments of the actual black hole collision correspond to the gravity wave, which are occasionally detected shown on the graph?
Yeah, that's a really good question. And so actually, the black hole collision often still happens many, like millions of light years away from us. So it actually, and the gravitational waves travel with the speed of light and actually get less high amplitude. So if you were very close to the black hole collision, you could maybe feel the wave, but to Earth it has kind of damped out. And so actually many of these black hole collisions have traveled for like millions of years before they actually arrive to Earth. Just because these events are so rare, they're often quite far away from us. Yeah. Good question.
Are the collisions directionally in a certain direction from us? I mean, are they all out by Orion's belt kind of thing that way? Do we know where we are in terms of the beginning and the end?
Yeah, that's a really good question. So we think they might be kind of in all directions, just because they're so far away is that like we don't actually kind of see them in our own galaxy, or we're not tracing galaxies, but they're just like kind of in random galaxies somewhere far away from us. But there's people trying to look for, we have some like localization that tells you like where in the sky they happened. With the current detectors, it's not so precise. So sometimes there's a collision and it tells you, okay, it was in this half of the sky. And you go like, okay, well, how to look for them. But there's people looking into whether there's maybe a bias or like a preference for which part of the sky they form, which would tell us something about how the universe evolved. But we probably need a little bit more data for that. Yeah.
So before I read the next one, we're going to wrap up our first piece, Columbia Astronomy and Astrophysics Work Events.
a little pen with all the colors. It says Columbia University Astronomy Astrophysics on the side. It writes very well. I did try it out. And so this will go to the terminal. Caroline Stun.
Caroline Stun.
Feels like too good to be
Okay, so the next question. What evidence is there that Big Bang was a singular event?
Ooh. I honestly wouldn't know. We have some evidence, I think, from just like we see the universe accelerated, but it's really hard to look all the way back to the Big Bang itself. We just don't have any observations of that. Like the closest we get is the cosmic microwave background, and so I actually don't think we exactly know whether it was like a singular point or not. I think we just see that it like expanded very rapidly. So at some point it was much smaller than we see today, but I don't think we know. Yeah, good question.
I don't know if I need this, but maybe everybody can hear me. So I was just going to say that, I mean, it's incredible as we study these things to, learn more about the universe itself and just our place in it and everything like that. So that in itself is just so valuable. But I was just kind of thinking, like, what might be a practical purpose that, the study of black holes or the study of the collision of black holes that we might be able to use all of this research for, into the future? Does it lead us towards some sort of business possibilities, some sort of, opportunities for, some scientific breakthroughs, whether it's space exploration or other kinds of things like what kind of things, because we're in the world of academia right now, and that's amazing, and we want to know these things, but what's a direction entrepreneurially or something like that we could take this information in?
I love this question, and so many thoughts. I should almost give another 3-hour talk about all the possible things we can do. But to just sample a few examples. One example is that actually these LIGO detectors, they're so sensitive. They're the most sensitive seismology aperture that we have on Earth. It's so sensitive it can hear, when the saying you never hear a falling tree in the forest or something? This one actually in Louisiana, it's close to a forest where there are falling trees several kilometers away. It can actually hear that. If a tree falls, it will cause noise in our detectors. We're very annoyed by that. Taylor Swift, when she gave a concert in Seattle, remember there was I think a news article that all the people were jumping so much up and down that it actually caused seismological meters to go off. It was actually first detected in these gravitational wave detectors because there's one that's 100 miles away from Seattle, but it actually picked up these signals. So we're learning a lot about the Earth, first of all, and random people jumping up and down. So that's interesting. But also these detectors, they're really sensitive. They have to measure such precise signals. So these are really as if you take the biggest lake, ask what's the volume of that lake, add one small cup of water, and then ask what's the difference in volume of water of this biggest lake. This is how precise these detectors are. And so you need to build very precise lasers, very precise mirrors, very precise mirror coding. And so these are all being used in other applications. My personal business model is a whole other story. You probably all know that you can buy or name a star after someone for $25. My dream, long-term dream project is to sell black hole collisions, to name a black hole collision after your lovely relationship. And then my simulation will tell you, how this black hole pair was created. So it's for real observation, because we're going to detect millions of them per year, right? So I only have to sell them for a few dollars. I can tell you with my simulation, hopefully by that time, how they were formed. So was it a very violent relationship that you almost break up, or did you stay together, and was it a very easy golden relationship? And so, okay, maybe I'll just do that for free. But I think that would be funny, a fun outreach, communication. A fun thing that I would like to know. I would like to have a black hole pair named after myself. But that's maybe we should talk about how to make that into a business model.
Okay, so I'm gonna wrap up the second piece of the
Woo!
This is a sticker with our Broekgaarden observatory on it. And I made this joke last time, and I'm going to continue making this joke until the roof is fixed. That this sticker is more structurally sound than Yeah, take care of the sticker, because this is probably the closest you're going to see it. We've observed for a little bit. And this sticker is going to Katie Wolf. Okay, next question. So this question, why do black hole pairs collide? Where do they really?
Oh, yeah, so really good question. The angular momentum is actually lost through emitting these gravitational waves. So these waves themselves carry energy, and so you lose energy, and that's actually how the pairs get closer and closer. Now, the funny thing is, why do they collide? So, okay, they lose this energy, but one really interesting thing is that actually, if you asked many scientists before LIGO find the first black hole collisions, is that there were many scientists who would say, you're never going to see something. We're wasting our money building these observatories because there's never going to be a black hole pair that collides and that we actually can observe. And the theory behind this is like, if you scale down, so to give an example, like why is this the case? It's like, if you scale down the universe by 10 billion, something I like to do all the time, then the sun actually becomes like about the size of, like a juggling ball, like maybe a little bit bigger, maybe more like a cabbage or like a coffee salad. Sometimes I bring cabbages instead. And so you have your stars are like maybe these juggling balls. Now, if you can calculate, okay, they lose energy through these gravitational waves, and they lose angular momentum, but it's only a tiny bit. It's very, very small. These gravitational waves are so tiny. So you can calculate, okay, if you form a pair of stars very early in the universe, say whenever the first stars form, so you have a lot of time to collide them. How close do I need to put the two black holes in order for them to collide today? So it takes 14 billion years for them to collide. It turns out that you need to put them like one solar radii apart. So imagine that this is one star, this is another star. They're just one juggling ball apart. And then if you have two black holes that are this close, they can they can collide, and they will collide only today, just in time for us to see it. Now, you could be saying, okay, that's fine. You just start with two stars that are that close to each other. They form black hole. You have your two black holes that are that close that can collide. The problem is these stars, you can start them out that close, but they actually become like 1,000 times their size during their lifetime. So if you start with these two stars, then one of the stars at the end of the slide is going to be like 1,000 times bigger than this juggling ball. So it would spin all the way to the end of the lecture hall. And it will just completely eat up the other stars. So they actually collide as stars, but not as black holes. And when stars collide, you actually don't see them through gravitational waves because they're kind of too fluffy. So it's not enough like gravity compacted. And so this is actually why a lot of scientists, I would say the majority of scientists were like, yeah, sure, stars exist, stars that close exist, but they just kind of die before they can be this like everlasting couple marriage and collide as black holes. So that was in the part. But it turns out that they can overcome this problem, and they do it in many different ways. So this is where all these different theories, they all kind of come up with some way in which they can overcome it. So one way would be to actually put them as black holes in these clusters, and that helps them come closer together later in life. But it's still a big question, like how exactly do they collide? Like how exactly can you form such a pair of black holes so close that it actually works out?
Hi, can you hear me? I think this is more of a technology question, but the sensitivity of the detectors is really pretty astounding. They have to measure unbelievably small changes in the gravitational field, or maybe more accurately, the curvature of space-time near the detector, as it varies with time. How is that done? What's the principle in which these detectors are constructed?
Yeah, that's a great question. And so the basic principle is that actually what Einstein already said is that light always has the same speed, so it has a constant speed with the speed of light. So whenever you have a laser and I point it at the end of the room, the time it takes to reach that room, and then if I place a mirror there to bounce back, is always the exact same in vacuum. So I can really precisely measure, if I shoot a laser, it will come back to me in the time it takes for speed of light to go back and forth. Now if I do the same in that direction for another arm, now if a wave passes by, actually what happens is that the distance between the mirror and me actually gets a little bit stretched and squeezed, and stretched and squeezed by less than an atom difference. And so what happens is that the light that I send in that direction actually takes a little bit longer and a little bit shorter to arrive back at me here on Earth. And so that tiny time delay in how long the laser takes to come back and forth, that's actually what we measure. And it's really hard because actually a mirror also itself also is made out of atoms, and those atoms also move. And so it's actually, you're trying to measure an atom difference in a mirror that also changes. But this is why it took like 60 years of building, improving, not detecting anything, and then eventually detecting it and winning the Nobel Prize, I think very well deserved for the eventual experiment. So yeah, and there's some tricks you can do to like make it a bit easier, but it's really, really hard. Yeah.
Okay, so we're going to wrap off the last piece of this.
Woo!
One more question on mine, and then you'll come up and ask all your questions one-on-one. So the last piece of merchandise is this Columbia University Astronomy and Astrophysics mug. Yeah, and also the rooftop observatory on here. And,
It's even more sturdy.
just like our roof filled with water and it's damaged, you can also fill this with water, but it won't get damaged. So something to look forward to if you can't see a little Columbia Astronomy mug. And this is going to David Trent.
Woo! All the way in the top. Good luck.
Okay. And the question is, so could you briefly explain in a bit more detail how your battleship simulations work? What actual measurements are you taking, and how do you know when you fix them?
Yeah, so that's a really good question, and I would love to say more also in person. But basically, we start in this 10-dimensional space where we try different hypothetical stars with different masses, different eccentricities, different like separations at the start. And then what we do is that we ask our simulation, how does this system, this pairs of stars, how does it live its life? How does it die? And does it die as a pair of black holes? And in most cases, our simulations, our factory will say, nope, disrupted, broke up during the supernova. But every now and then it will say, yeah, this made a pair of black holes, and that's what we call a hit. And then what we do is then, when we find these hits, we tell the machine learning algorithm to like look around it. So like what we do is we kind of define like a Gaussian distribution or like a distribution or kind of sphere around that point with a certain size that we say, okay, look, try more points there and try to like uncover which exact properties can give rise to this pair of black holes. So that's how it works.
Cool. Okay, so thank you for all your wonderful questions. And another
Yeah.
round of applause for you and for Dr. Broekgaarden.
Yeah, thank you, everyone. Reception.
Okay, so we're going to break now. You can come up, ask what are your questions, ask any of the astronomers in the room any questions. We do have eclipse glasses to give away for anybody interested. So I think Jen and I will be handing out eclipse glasses if you come down here.
Yeah, and don't forget to look at Orion next time you see it in the sky.
Yeah. Also, yeah, we really appreciate your feedback. So
wanna do here?
be sure to fill out the Astro exit ticket on the way out. Thank you.
Gravitational waves? Yeah, they think so, actually. Well, it depends where it is, but yeah, if it's usually it's far away, right? So usually it's somewhere far so it just looks like less bright as like a star, like it kind of outshines a galaxy. You already don't see galaxy, like with your naked eye, it's hard to even see one galaxy. So then it's like that's supernova. If it happens in a nearby galaxy, you can see this on the sky. It just looks like a normal star.
But I'm saying for Betelgeuse.
Oh, that one. I think it's still quite far. Like you would definitely, it would be really bright. Like you could even see it during daylight, but it would kind of look like still small, much smaller than the sun, just because it's so far away. So I think you can see it with your naked eye, but even during daylight, so that it looks kind of like a planet, probably. Yeah, like Venus or something. Yeah. 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 so this is a really good question. And so actually we can see all the way until basically it's like a still. So even when they are together, it kind of like rings a little. You know, just like if you have a hammer and you ring like a bell, it kind of still rings. So we actually can see all the way until it like ends up ringing and it becomes like a boring still black hole. Yeah, it's really. It's like within millisecond, like less, you know, super tiny seconds. But we can also see like basically, so you have some point where they're touching and it kind of forms like a figure 8 shape or so, and like, or this like penis shape. And so we can actually measure that, not so well because it's just like there's a lot of noise too and it's very short signal. But people are trying to model it, like what it looks like, and we don't fully know. So we actually think that these observations are going to give us the answer.
The spherical